So hybrid, I think you can click more.
I think it's fine. Yeah. Okay.
Yeah, I mean, maybe, I guess it's fine.
Yeah. Yeah. Yeah, let me start.
Yes.
Yep. Okay, hello everyone. My name is Seungchan Kim, and today I'm going to give a thesis proposal talk titled Spatial Reasoning and Semantic Representations for Intelligent Multi-Robot Exploration and Navigation. Before I start, I'd like to thank my thesis committee members, Sebastian Scher, Jonathan Bisk, Vanita Bibb, Graham Best, and Michael Kroll. Let me start with a short video clip of autonomous robot that's exploring inside environments like buildings and caves. The autonomous robot has to perceive its surrounding environment using onboard sensors, plans its own next actions by using policy, and then have to incrementally map the environment without having any prior knowledge about the environments. This is the type of setting that I'm interested in today. Why are we interested in autonomous robot exploration? Well, first, robots can explore areas that are dangerous or difficult for humans to reach, such as disaster zones and chemical plants. Also, autonomous robot systems can enable efficient, large-scale mapping of complex environments. And there are many applications, including search and rescue, environmental monitoring, and industrial inspections. In particular, in this thesis, we are interested in multi-robot explorations. Why do you care about multi-robot exploration? Well, first, multiple robots can definitely cover larger areas more quickly than a single robot can achieve. And even if one robot fails, the remaining robots can continue the missions, thereby increasing the resilience of the overall missions. And sometimes heterogeneous robots can perform a variety of tasks simultaneously. What makes multi-robot exploration particularly hard? In multi-robot explorations, the coordination of the behaviors of multiple robots is quite challenging, and especially under a decentralized scheme where there's no central entity that makes plans based on the global data. Each robot has to make its decisions based on the local information, which makes things even harder. Another aspect of multi-robot exploration's challenge is communication constraints. Limited communication range and bandwidth often restricts connectivity across robots, which often leads to suboptimal coordinations. Also, task allocation for multiple robots in a diverse set of environments is non-trivial. Lastly, building robust and shareable representations across robots still remains a significant challenge. In my view, multi-robot exploration can be enhanced by or improved by following steps. First, each robot has to have a good local understanding of the environment. Second, each robot has to plan its own actions by fully exploiting the local information. Next, robots have to share their own environmental understanding with each other, even under the condition of limited communication constraints. And when robot has to plan, it has to plan with awareness of other robots' actions and understanding. This is how I view multi-robot exploration can be enhanced. There are two paradigms of environmental understanding. First, spatial understanding, and second, semantic understanding. Although these two concepts are not strictly dichotomous, spatial understanding are related to properties that pertain to geometry, locations, structures, distances, layouts, occupancy, and arrangements. Whereas semantic understanding are more related to properties that pertain to meanings, labels, objective information, and categories and language descriptions. And using these two spatial and semantic understanding, in this thesis, we try to leverage this understanding for the sake of planning and multi-robot coordination under the context of multi-robot exploration and navigations. Let's quickly go through the problem formulation first. In the case of single robot problem formulation, it's just a very common notation where state is evolving from previous states and actions through transition dynamics. And observation is an output of sensor models in the states. Here we introduce map representation MT, which is the output of the processing functions and observations. And action or control inputs are driven by the policy that depends on the map representation and states. Our goal is to find a trajectory that maximizes objective. And here the objective can be exploration objective, which is often measured by covered area given time or map accuracies. Or this objective can be navigation objective, which can be measured by success rates of finding target objects or trajectory length. And in this thesis, our focus is on the integration of perception and planning here. In the case of multi-robot problem formulation, things are very similar in that each robot has to have its own state, observations, and local map representation. But there's an additional component which is sharing of this representation when communication is available. Robots have to share this representation with each other. Then the action or control input is driven by the policy that depends on the global representation and states. And our goal is again to find trajectories that maximize objective collectivity in this case. Again, the focus is on the sharing of representations. There are many prior works in multi-robot exploration and single robot explorations. On left side, there are some works that have focused on large-scale multi-robot explorations, such as in Scientific Challenge. However, these methods have been focusing on frontier-based exploration, and they shared a large volume of map representation each other. On the other hand, in the middle, there are some works in multi-robot exploration that aims to find communication-efficient representation to be shared across robots, such as Gaussian models, but these have been focusing on the spatial representation only. On the other hand, there are some works that leverages semantic representation, often tackling object-level navigation. And this works has lots of works here, but they are mostly confined to indoor small-scale navigations with single robot experiments. This is a Cartesian diagram of how I view my thesis lies in the context of prior works. On the y-axis, there's a number of robots, and the x-axis, there's exploration task spectrum or complexity of objectives. And in the first quadrant, there are traditional works like Yamauchi et al., which is conventional work that relies on frontier-based exploration. On the top, there are some works like multi-robot exploration with large-scale mapping, often relying on frontier-based explorations. On one hand, there are some recent advances in robot exploration with advanced representation and complex reasoning that borrows concept from computer vision and NLP also. And my goal is to address this final quadrant, this multi-robot exploration with better reasoning and better representations. So this is the thesis statement of today. Leveraging spatial reasoning and semantic representations enables multi-robot systems to improve exploration efficiency and navigation success rates in diverse environments. In order to validate this thesis statement today, I'd like to go through the following chapters. Here are completed and proposed works or overview of the table of contents, which is divided into spatial reasoning and part 2 semantic representations. First, as a subpart of spatial reasoning, I'd like to focus on the geometric analysis of the space. How can geometric analysis help multi-robot indoor exploration? That's my completed work 1. Next, I bring the concept of map predictions. How can predicting the spatial layout of the unseen parts of the space help the exploration in the case of single robot exploration? And then we extend that to multi-robot exploration for my proposed method. And then we move beyond spatial reasoning and go to semantic representation. The first question I address in semantic representation is how to allocate tasks for multi-robot heterogeneous semantic search. And finally, I address the question of how to build online semantic scene representation for more complex language-based reasoning and planning in the context of multi-modals. So having that in mind, let's move on to the first chapter, which is geometry cube extractions. So let's first see this video of Tom Stroh that enters the doors or passageway through, and then observes some information about the rooms inside, spending enough time inside and collects information within the rooms. This is the type of exploration that I'm interested in this chapter, in indoor environments. So in this chapter, we focus on the room-based exploration or room-focused exploration. There are some reasons. Well, in general, meaningful target objects are more likely to be placed in rooms than other areas like corridors and hallways, thus need more focused attention. And rooms often serve as structural segmentation units that constitute buildings. And the question that we address in this chapter is how can you coordinate the behaviors of multiple robots that are exploring in a building composed of multiple rooms? In order to address this question, there are many sub-questions such as how can you detect doors and rooms, how to behave within the room to explore or fully observe this information, and how to find a room that was not observed by other robots. The key idea is that we make the robots to actively search for geometric cues that represent doors and rooms. In the case of frontier-based exploration, what robot does is to select, identify the frontier between known and unknown spaces and select the nearest frontier points. Whereas in our approach, we aim to robot to actively search for cues that represent doors and make that as the next waypoints to go. In this chapter, we used LiDAR as a primary sensor, and we had customized drone with Velodyne LiDAR sensor. Because that makes sense because we focused on extracting geometric properties of the environment. This is the perception pipeline of the first chapter. In indoor environment with multiple rooms, the robot generates 3D occupancy boxes from 3D point clouds from LiDAR sensor, and from which it generates 2D occupancy grid maps. And then robot converts that into 2D distance transfer map. The first question that we have to ask is how to detect doors just using LiDAR and just leveraging spatial properties. The answer is we reason on the 2D distance transfer. If you think about the top-down view of the drones and the walls from the top, and if you also think about the distance to closest to occupied cells, and let's say that this point in the middle represents the drones. Along this red axis, this point in the middle is the farthest point than any other points on this axis in terms of the closest distance to occupied cells. So therefore, this point is local maximum along this axis. On the other hand, this point in the middle can also serve as the closest point to the occupied cells compared to all the other points on this blue axis, which is perpendicular, right? So this also serves as the local minimum along the perpendicular axis. Therefore, this point is local maximum and minimum at the same time, which means we can detect saddle points in the distance transform, and that is almost equivalent to the doors. So the idea is that we can detect doors by extracting saddle points, and we can get saddle points from these determinant equations. And then using this, you can actually detect all the locations of doors in the indoor environments. And for the planning purposes, we just simply assign the saddle points as the next waypoints to go. Rather than just making robots to randomly explore using frontiers, we directly set the robots to go to the doors first. Another geometric cues that we can get from distance transform is local maxima. And using this local maxima, which is derived from this equation here, we can represent the free space into representation of the circles, where each point or center of the circle is local maxima, and the radius is from the closest distance to the wall. And why do we want this kind of circles? Well, the rationale behind circular decomposition of room space is that we don't need an accurate representation for rooms or polygons, just rough approximate representation like circles suffice. And making just by reaching the center of the circle, robots can obtain sufficient information about the room. And there are more details of the circle splitting mechanisms in the case of big room, where sensor range is smaller than the radius. Okay, so using this idea of geometric cues of circles and saddle points, let's talk about the path planning for robot exploration. The algorithm is that instead of choosing nearest frontiers, robot aggressively look for saddle points in local maximum distance and perform circular decomposition. The robot chooses the doors to go and then observe the circles and repeat this process, thereby generating a path like this. In the case of multi-robot coordinations, things are very similar. The first drone actively searches for these doors and then observes this circle. And the second drone can communicate with this first drone, thereby sharing this information with the first drone. And then this drone also looks for the next target saddle points that can be detected. Goes there, observes the rooms, another drone also observes the room. And using this technique, only by sharing concise geometric cues like saddle points and circles, robots can coordinate their behaviors, avoiding redundant explorations. This is a video clip of multi-robot coordination or target assignments. For the sake of communication, each robot updates and shares the list of doors or saddle points that are reached by itself, a set of circles it has reached, and a set of circles other robots have reached. The idea is that target assignments are based on those shared representations, and the saddle points and circles are very memory efficient and concise representation of doors and rooms, which helps communications. For the experiments, we performed experiments in 8 different gazebo environments, which includes some challenging scenarios. And the baseline was sub-T UAV exploration, frontier-based exploration baseline. And we tested up to 3 aerial robots. And we measured the number of surface voxels in the rooms that were observed by the robots collectively. This is the qualitative behavior comparison with baseline. The baseline, as expected, it doesn't prioritize going into the rooms, whereas in our case, the robot turns its way quickly and then look for doors or saddle points and go inside the rooms and look for information there and goes out and seek for next rooms. In the case of more rooms and multiple robots, the baseline does sometimes skip some rooms and sometimes the robot go into rooms, the same room that other robot has visited. But in the case of our methods, the robot avoids redundant explorations and doesn't skip any rooms. This is the quantitative results of 2 robots room exploration and 3 robots room exploration comparing our method and baseline in terms of number of observed voxels in the surface of the walls in the rooms across time steps. And this is a short video clip of real robot experiments where there are 3 robots, aerial robots, communicating each other, sharing the information they has gained, saddle points, and everything, the geometric cues that they detected. And this is further real robot experiments video of detecting many rooms in these indoor environments. So the takeaway of this chapter is that we proposed autonomous exploration pipeline that coordinates the behavior of multiple robots in a building composed of multiple rooms. And we use just geometric analysis to extract saddle points and local maxima for door and room representations. And we validated our method in simulation and real drone experiments. Having this chapter done, let's move on to the next chapter. How can we use or leverage map prediction for the sake of explorations? So let's think about the robot exploration in indoor environment, and our goal is to have a holistic understanding of environments. Well, in this case, in fact, the robot doesn't even have to visit every single room in the first place. Like, if the goal is to gain more understanding of holistic understanding of the environment, maybe the robot thinks that, oh, maybe I don't need to visit every single room. In fact, humans can predict the structure of the indoor floor plan without observing the entire space. For example, if you see this image, even without going inside the rooms, you can decently predict what's ahead, what's beyond your observation. You can imagine what's beyond these rooms. Humans, by observing partial information such as door locations and corridor width, they can predict the environment's overall layout, spatial layouts. And we want the robots to have such map prediction capacity as well. And the question is, how can such map prediction enhance exploration? When the robot has to make a decision between these 2 frontier points, and let's imagine that the robot can have some map prediction capacity. Here, on the top parts, the robot has quite high confidence in the predictions, and the estimated area to be covered according to the prediction is quite small. On the other hand, in this bottom part, robot is quite uncertain about this prediction, so therefore low confidence in the predictions. And it's more likely to cover more areas in this case. In that case, we want the robot to choose the bottom ones, not choosing the top ones. In a nutshell, robot can explore areas with high uncertainty and more potential information gain. There are some prior works on map prediction-based exploration, such as UPenn or iJector. Both prior works leverage learning-based map predictions, but they're different. UPenn reasoned over uncertainty of the predictions by modeling the uncertainty using variance map, but there was no reasoning on the potential sensor coverage. On the other hand, iJector used coverage as information gain metric and didn't reason on the uncertainty. Our approach is to predict maps and jointly reason over coverage and uncertainty. And our insight was to use image implanting network from computer vision for the map completions. If you see this image in the middle, there are some occluded parts by white parts, and using image implanting, you can complete this map, complete this image because image implanting can fill in unseen, occluded, and missing regions. The idea is, can we use this for indoor map predictions? And the answer is yes. We predict 2D top-down view occupancy grid. This is what you see on the left side is the 2D top-down view observed map or observed occupancy map. And by feeding this map into the llama network, we can predict such descent prediction, which is quite close to the truth. The idea behind it is this: we fine-tuned llama network or image implanting network using T-teach fluid data sets. So this is the MapX framework that we proposed recently. Given the 2D observed occupancy grid using the map predictor or llama network, we generate a set of independent map predictions. We call this ensemble of predictions. And from this ensemble of predictions, we generate 2 things. First, average of those predictions, or mean predicted map, or variance map, or uncertainty map, which is pixel-wise variance of the predictions. Let's think about how much information gain each robot can get at certain frontiers using this mean predicted map. What people usually do is that when the robot thinks that it plans to go to this red point here, what people usually do is that they first think about the raycast with only using observed occupancy grid. However, Since there are some walls behind, this often overestimates the information gain. The other option that we can try is to have raycast with a predicted map. However, this is very susceptible to wrong map predictions and often underestimates the information gain. We want to find something in between. The key idea is that we use a thing called probabilistic raycast on predicted map. As I said, there are 3 independent predictions like this. And we have mean predicted map or average predictions. From this point, from this red point, we generate hypothetical raycast. And if we do not use probabilistic raycast, this raycast stops here. But instead of making it stop here, we still let this raycast go and let raycast stop at certain threshold. This means the raycast starts at delta value 0 first. And then whenever this raycast hits the values in the mean predicted map, it adds the values here. And when this value is over the certain threshold, epsilon, then the raycast stops. And we do this for all the raycasts over 360 degrees. By doing so, we can generate a visibility mask or probabilistic visibility mask. We generated visibility mask using a probabilistic raycast, which represents the information gain you can get. And using the uncertain map or variance, we have information gain metric that is summation of the variance of the points that lie under this visibility mask. Using this new information gain metric, how can we improve exploration planning using predictions? In the case of nearest frontier exploration, the robot chooses the closest unvisited frontier. That's traditional way of choosing the frontiers. But in this case, in MapX planner hours, robot chooses the frontier with the highest information gain that considers both uncertainty of the predictions and estimated sensor coverage at the same time. So this is the MapX framework that starts from the observed map, predictions, and calculating the probabilistic information gain and path planning using Frontier Explorer. For the experiments, we did simulation on the KTH datasets, and the baselines are the 2 prior works that we proposed, that I introduced, UPenn and ijector. For the metrics, we had three metrics. First, coverage. Second, predicted IOU. And lastly, it's topological understanding, which is a new novel metric that we proposed for the sake of downstream pathline tasks. So as for the qualitative behaviors of MapX, when the MapX has to choose between these purple points and orange points to choose, even though the area or information gain that it can get at the purple point is larger, the robot choose the orange one because it has higher uncertainty. On the other hand, in contrary, in this case of this scenario, the robot chooses the orange one, not the purple one, even though the purple one is closer because orange one has higher coverage and similar uncertainty. This is qualitative comparison with baselines, including UPenn and ijector. UPenn is known for optimizing and reducing uncertainty of the maps, and ijector is known for actively searching for sensor coverage, but is susceptible to wrong map predictions. Whereas MapX, our method, jointly reasons on both uncertainty and sensor coverage. This is quantitative comparison between MapX, UPenn, ijector, and nearest frontier. As you can see from this graph, in terms of coverage metric, IOU, and TU success rate, in all metrics, MapX outperforms the previous baselines. The takeaways of this chapter is that we propose a novel framework for exploration in indoor environments that leverages the idea of map predictions. And our framework uses a technique called probabilistic information gain by reasoning on both sensor coverage and uncertainty. And we did simulation experiments on real-world floor-plan datasets and showed MapX outperforms state-of-the-art methods. Okay, so I think this done. Let's move on to the proposed method today. So how does such prediction help multi-robot indoor exploration? How does map prediction help multi-robot indoor exploration? So in the case of multi-robot indoor exploration, we add another condition, which is communication constraints here. For more realistic setting, we consider base station at the starting location, and also robots can communicate with each other and base station if they are within the communication range. So this is the problem formulation of a multi-robot case of predictions. So multiple robots explore indoor environments, the same environments in a decentralized manner, and the base station is fixed at the initial location of the missions. And there's a robot-to-robot and robot-to-base station communication if they are within communication range. and information received by the base station only counts. And the goal is to generate trajectories of multiple robots that maximize the understanding of the environment collectively. And this is two models of communication conditions that I can have in simulation. First case, more circular range. If two robots are within the threshold distance d, it's a correct, it's a communication on. And the second case is we also consider about like more blockage or optical cells. How many optical cells are there between these two robots? So we will consider these two communication conditions in this chapter. And let's think about the limitations of the current approach. So what is the current approach? When we run each robot independently without any coordination, they follow the single robot strategy, which often leads to redundant exploration. This is something that we do not want. Well, another good strategy is to split at first, which can cover different areas at first, right? But in the case of multi-robot coordination, we need some sort of in the middle or interim communication that is needed for coordination. Such meet if lucky strategy sometimes hinders the effective coordination. And initial splitting may optimize for short-term coverage, but can lead to redundant revisits in the long term. What about fixed rendezvous approach? Does this help? What about the fixed location for the rendezvous? The problem is that there's much uncertainty on the plausible locations of the rendezvous points. There's no guarantee that these points there will be a feasible path to these points. What about the predetermined time? Context-free scheduling may cause inefficiency in exploration, such as robots waiting unnecessarily. So my proposed approach in this chapter is to leverage map prediction to overcome such communication constraints. First idea is to augment exploration with shared map predictions. In the case where there's no predictions, even if the robots communicate, robots only share observed occupancy grids, past trajectories, and some myopic intents. But in the case of predictions, robots can augment their perception with predictions. And robots also share those predict maps with each other, which can make the robots, each robot can use the other robot's prediction as if this is the robot's real observation and use it as an input to the prediction model, enlarging the size of the predictions. And using this, robots can generate long-term estimation of other robots' trajectory via multi-step rollouts. So this is the first idea that I have regarding augmented exploration using shared map predictions. Next, it's about dynamic random estimation using predictions. We want the robots to estimate the location of the rendezvous dynamically during the missions, and robots have predictions like this, and they might be able to identify the potential points where they can meet in the middle, such as the red check marks here. But as robot moves along, it has more observation, which leads to more predictions, and it can dynamically update the likely rendezvous using predictions, which will change the location of the rendezvous in the middle. And there are potential methods such as heuristic-based decisions heuristic-based decisions or learning-based strategies. The proposed planning scheme for multi-robot exploration using prediction is different from single robot planning, because single robot planning, it only chooses the frontier with the highest information gain using predictions. But in the case of multi-robot planning, we want the robots to choose frontier with high information gain, at the same time closer to estimated rendezvous areas. The evaluation and metrics are here. As for the data sets, we use the same simulator from the KTG dataset, same with the previous work, but with 10 larger environments. For the metrics, we will measure the collective coverage and predicted IOE over time that was sent back to the base stations. For the baseline comparisons, each robot performs frontier-based exploration, respectively, without any communication. The second, multi-robot performs MAVEX individually, but there's no meeting the middle strategies. Lastly, each robot performs MAVEX with fixed rendezvous points and schedules. The expected contribution is as follows. This will be the first research work that leverages map prediction in the multi-robot exploration settings. The idea is to overcome communication constraints, which are the unique challenges in the multi-robot exploration in indoor settings using spatial predictions. And using predictive mapping, robots will be able to explore the environments more quickly without much redundancy. And furthermore, we'll be able to estimate likely rendezvous areas to meet for communications. Okay, having this done, let's move on to the second part of today's talk. Let's move on to semantic representations. First, I will address how to allocate tasks for multi-robot semantic search, and then I'll talk about online semantic scene representations for management. Okay, let's think of a search and rescue scenario in outdoors. There are some debris, collapsed buildings, or there are villages in the back. There are rocky areas or forests. And in order for the robots to do the following task prompts, such as search injured person near the rocky area, the robot first has to go to find the rocky area first, and then go there to do some local fine-grained search. If the prompt is search, find any signs of fire in the forest, it first has to go to forest and then start looking at the forest or trees and look for signs of fires. In the case of this, search for injured people near the collapsed building, the robot has to first identify the collapsed buildings, go there, and then start looking for people there. The idea is that by decomposing the global area into subregions, it opens up the possibilities of hierarchical search and explorations. The problem formulation of this chapter is as follows. Multiple drones are performing collaborative outdoor search and navigation missions, such as search and rescue. And there's a strong assumption. Human operator provides structured text prompts dynamically during the missions. And all prompts are in the form of following: find objects of interest in region of interest, such as find injured people near the crashed buildings or search for vehicles in the river. We'll drop this assumption next chapter, but for this chapter, we'll focus on these strong assumptions. And the type of objects or region of interest can be very flexible or descriptive terms like crashed buildings or forest region, not just building. And for this, we need semantic representations. So let's dive into some related works of robot exploration and navigation in semantics. On one side, there are some works on object-goal navigations proposed by Chaplin et al. It was trained on code set object detector and used policy using trained semantic priors, but it was confined to mostly indoor and single agent navigation. In the middle, there's a recent work from Yokoyama et al. It did open set object search with frontier-based exploration, and it generated value maps with VLM features. There's also recent work from RSS, where they performed real robot inspection tasks using semantic network, but there was a assumption such as floor plan as a required prior. Many previous works have focused on indoor single robot object search navigation. However, in this chapter, we aim to address multi-robot outdoor navigation with open set target goals. The insight is that using vision language model, you can generate language aligned or text image aligned features of the image. There's a drone here, and it views the scenes like this using ZX camera. And using VLM encoder, you can generate image text aligned features like that. And this image text aligned features can be compared with any text prompts, because we can feed this text prompt as well to the VLM and generate feature embeddings of this text and perform cosine similarity search between these two. The point is that the feature embeddings of this image are agnostic of feature queries. And we can compare the similarity of image and any text prompt in the same feature space, since this is text image aligned feature embeddings. We project language aligned features for 3D voxels. We first generate 3D voxels using LiDAR, and then we project VLM features to 3D voxels. Then we compare each voxel feature with text prompt features, and then we highlight the areas that text prompt wants. This is preliminary proof of concept tests on real world data. We first generate 3D voxels of the environments. And using this, we can project VLM features to these voxels. So 3D voxels with VLM features projected. And given, by the way, we are using a model called NACLI or NACLI. And we perform cosine similarity matching with features of text. As you can see here, if we give prompts like in red building, it highlights the areas that correspond to the red building in reality. For forest areas, if we give the text from forest, it highlights the areas with forest. How good is text image alignment for our purposes? I tested with NACLI, one of the VLM model features. Given this image, when I gave the list of text prompts, we can quite decently well detect the areas that's corresponding to the real world. For example, if you give prompts like grass, it highlights the areas like grass. What's in the middle is I gave some arbitrary concept like container. In fact, this is not exactly the container. This is more like mixed drones, but it's very similar to container, which makes sense. Also, it can detect things like traffic cone, which is very small objects. So I think this can be used for text prompts containing open set vocabulary. This is my proposed planning and coordination approach. Multi-robot hierarchical and heterogeneous semantic search and explorations. The key idea is to have heterogeneous task allocation among robots and perform hierarchical search. So first, one drone performs global scouting and region segmentation, and then other drones perform more fine-grained local search and navigations. Given the prompts like find crashed car near the lake or find signs of fire in the forest, the robots have to go to the lake or forest first by communicating with the first drone and go there and start searching for local navigations. More formally, there's a leader drone R1, the worker drones are 2, 3, and so on. And there's a set of prompts where each prompt is structured as object of interest and region of interest, given from the human operator at the base stations. If the prompt is given from the base station, it can directly reach to the leader drone, or it can also go to the local drones, depending on the situations. But all the decision is made by the leader drone here. And the leader drone extracts the information about the region of interest and highlights the area that corresponds to this region, and send this task to the local drone that's close to this area. And this drone perform local fine-grained search and navigations. So divided task allocation between robots are there for semantic search and navigations. So it's composed of 4 steps: prompt receiving, text voxel feature matching, subtask coordination, and local navigation. And we have different task allocation for leader drone and worker drones here. Step 1 to 3 is assigned to leader drone, and step 1 and 4 are given to local drones. There's a caveat that language-aligned feature projections of voxels are quite memory inefficient. If the robot generates VLM features, for example, each voxel has very large feature dimensions, such as in the case of NatGrid, 512 feature dimensions, which is a lot. And considering the number of voxels in this environment, and the number of voxels incrementally increases along the navigation, number of voxels times feature dimension is a very large volume of data. And maintaining and sharing all these representation with other drones is inefficient. So for communication, we need more concise and condensed sharing of information. And I plan to leverage clustering methods such as agglomeration clustering to group voxels. So here's the proposed evaluation plan. As for the data set and simulator, I will use AirStack, which is a customized drone simulator with photorealistic isosim environments. And we'll try with 10 different outdoor environments with customized text prompts. For the real robots, we are recently building Ascent Street Drone with customized payloads. This contains Orient HX and ZX. As for the metric, we'll measure the success rate, which is the number of objects found in the given mission time, collectively by robots. For the comparisons, we'll first compare with very simple baseline method, which is pure spatial and frontier-based exploration, but equipped with open set object detection pipelines, such as the one we stand. And the second comparison baseline would be multiple robots performing search guided by VLM features, but there's no hierarchical or heterogeneous task allocation at all. The expected contribution of this chapter is that this will be the first research work on multi-robot or multi-drone outdoor semantic exploration navigation framework that focuses on the search and rescue scenarios. The key is heterogeneous task allocation and coordination, leveraging VLM features, which can support open set vocabulary text prompts. And the limitation is that this prompt structure is quite restrictive and human prior is required. Okay, having this done, let's move on to the final chapter of today's talk. How can you build online semantics representation for language-based multi-robot reasoning and planning? So the limitation of the previous chapter was that we assumed the existence of structural text prompts, such as find objects of interest in region of interests. Although this assumption is practical and applicable to real-world deployment, these prompts heavily rely on the human's prior knowledge. For example, you have to go to there in order to find something, right? And moreover, we didn't fully exploit the semantics, languages, or semantic relationship between objects for reasoning and planning, because that was already given by these prompts. Can you do beyond more than cosine similarity matching? to answer these questions, I raised this question: what is more general semantics and representation that will enable more complex reasoning and planning? What is more general representation that can be robust to any natural language task or queries? And what are the types of some examples of more complex reasoning and planning? The example prompts could be like find injured humans in general, or locate all exits of the red building. What is a safe route to exit the area? In order to answer these questions, the robot has to leverage deeper semantic insights and contextual relationships. And what information should be there captured in the representations? Not only the spatial properties, but semantic information such as context, text captions, scene descriptions at varying levels of granularity are required. My insight is that we're going to build semantic scene graph that captures essential information about the environment, like scene graph. Scene graph captures local information from to intermediate level and higher global level, and we'll extend that to multi-robot settings. And each robot is building scene graph at the same time. Let's quickly go through the related works on scene graphs. Hughes et al. That was 3D semantic, very famous work that does 3D semantic scene graph generation for SLAM, but it was confined to closed vocabulary and was processed offline. The one in the middle is concept graphs that enables open vocab detection, segmentation, and supports LLM-based reasoning, but it's also offline-based and indoor and single-agent planning. Recently, there's another work called Embodied Reg that captures multi-layer summary of the environment by injecting text caption, just text captions from VLM initially, also focusing on indoor and single agent. In this chapter, we aim to build general online representation, not offline, for multiple robots in the outdoor sense that can be robustly adapted to downstream tasks. So problem formulation of multi-robot online scene graph is simple. So state observation and scene graph is similar previously. And for the exploration task from task, we want to make a policy that following this exploration and prompt tasks. Exploration is more on the building representations, and prompt is more about answering the questions or search and navigations. And there must be communication between these two graphs. Sorry. For the proposed approach, we're going to use online scene graph with dense VLM features and text captions for now. So first, robot generates dense VLM features for each voxels. And using clustering techniques, group voxels with similar features are grouped. And the average of features or position of these features sets are captured. And along with this, we also need some text caption to store in each node, which will be it would be great if we can generate captions directly from the features, but it's not possible for now. Instead, we'll use VLMs to generate captions from ego view images and save this information at the nodes and generate scene graphs. There's alternative proposed approach to generating graph node, which is following the concept graph approach, which you first use zero-shot instance segmentation first to segment images, and then putting this segments each last into VLMs to generate features, and then project that into 3D voxels. This will generate more object landmark node for graph. This is very similar to concept graph approach. At this moment, I'm not sure whether the first one or this one is better. We'll compare this both with the previous approach in terms of granularity, computation, and memory efficiency. There are some further thought points on the graph structures. Edges should encode a spatial relation between nodes, such as some object is on top of this, or some object is 50-meter distance behind. And still, there's open questions such as how much hierarchy do we need? How many layers of hierarchy are required, and at what levels of granularity? Previous works like this have different concepts. Works like Hughes et al. It had indoor environments, and there are 5 levels of structures, but indoor environments have clear hierarchical structures in the first place. Concept graph doesn't have hierarchy in the graph structures, but use plain graphs connections to feed that into LLMs. And my proposed approach is for more complex reasoning and planning, we leverage large language models. Each node capturing object information, caption features, the edges, capturing relationships, convert that into JSON data format, feed them into the LLM. The LLM will also receive text forms, as well as the JSON data format of the scene graphs. we want LLM to serve as a planner. So since LLM is not a black box planner, we first generate scene graph and put that into JSON format, where each node has captions, object types, attributes and positions, and edges representing spatial relations. And we feed that into LLM with query prompts. In the case of simple tasks, it could answer direct text answers, which is the simplest case, or it can generate simple actions in the form of waypoint generations, such as outperform the 3D positions of waypoints. In the case of more complex tasks, it requires more multi-step chain reasoning or collaborative reasoning. Output form should be subtasks of this complex tasks. And how can we leverage partial graphs or online partial graphs for multi-level planning? Each robot is observing local area of the environment, hence this is a partial graph, not global, not the environments. And there are some challenging prompts that require robots to collaborate. How should they collaborate with each other? There are some types of challenges that require multi-robot coordination. For example, there are some cases in which robot doesn't have access to the information beyond its observation, but can ask if other robots have already observed or are aware of the specific areas. For example, find injured humans in the forest, but it didn't have any information at first. It only has observed what can also be done. So let's ask if other drones have already explored it. Or there's another type of task, such as tasks that require multiple robots collaborating and dividing subtasks. For example, locate humans and find potential paths avoiding grassy area. And in this case, one drone might detect humans, and the other drone just focus on detect grassy areas. And in terms of sharing representation across robots, we want to be very communication efficient, and robots don't need to share the entire graph. For the communication purpose, only the text captions portion or sub parts of the graph or just answers to queries are shared across robots. And for the evaluation metric, dataset and simulator, we use same air-stack simulator with Isaac same photorealistic environments. However, the text prompts should be designed to be more complex and challenging than the previous chapter. For the metric, I'll measure the prompt task success rates, which is ratio of number of successful prompts divided by total prompts. The secondary metric that I want to measure is the quality of online scene graphs compared to offline processing. The offline processing version could be thought of as ground truth version of scene graph, which serves as the upper bound of the accurate scene graph. For the baselines, method with task prompts just with constant similarity matching will be used, and we'll compare with offline processed version of graph for upper bound estimations. The expected contributions of this chapter is that this will be the first research work to address multi-robot and online semantic graph representations, contrary to previous approaches that focus on offline generations. And by leveraging VLMs for representation generations and using LLMs for more complex reasoning and planning, we will be able to see unique challenges on online partial graph as opposed to global offline graph. And this online partial graph assumption fits with more multi-robot settings, which requires communication and collaboration using graphs. Okay, so I'm done with the proposed works. So this is my timeline for my proposed works. So for the proposed work one, I will spend 3 months aiming for iOS until March. And at the same time, I will work on proposed work 2, which I aim to be complete by the middle of next year. And then I'll work on the proposed work 3 by early next year. And then I'll write thesis at that time. Okay. So as a concluding remark, I'd like to go over my thesis statement again. My thesis statement was leveraging spatial reasoning and semantic representations enables multi-robots to improve exploration efficiency and navigation success rates in diverse environments. And to validate this statement, I showed some completed works, some ideas on the proposed works, like geometry queue extractions, map predictions for communication constraints overcoming, and using heterogeneous task allocation using semantic features, and online scene graph for complex reasoning and planning. So this is how I'm going to prove this over the next 1.5 years. Oh, thank you so much for listening to my presentation, and I will start getting questions. Thank you.
Thank you, Seungchan. So I guess we'll start with Brandon because we still have this earlier. Maybe work our way closer.
Sure. Hi, can you hear me?
Yes.
Yes.
Hi, Seungchan. Yeah, thanks for the talk. Very clear talk. Also good to see lot of kind of good ideas happening there. So planning, perception and planning, but also kind of the spatial representations and semantic representations and trying to see how all that fits together. So that's really cool. Have a couple of quick questions. So for the first one is, in the first part of your talk, there was a lot of what you're doing was about uncertainty and noise, right? In the second part of the talk, I didn't quite see how that would fit in. So my question here is, so with these semantic representations, presumably there's going to be noise there as well. If there is noise and uncertainty, how would you plan to address that?
Yes. As for the uncertainty and the noises, I think you're talking about the map prediction exploration parts, right?
Yes. So in the first part, yeah, you got the map prediction, you kind of got this filtering stuff. Like a lot of it is about noise and uncertainty. I just didn't quite see that same thing come up in the second part.
It would have been great if I had incorporated uncertainty concepts or like predictive, like probabilistic, like semantic representation for the second parts. But for now, I'll just focus on generating those semantic representation without considering much about the prediction, like uncertainty. But there must be some kind of like threshold reasoning or like confidence reasoning that should be incorporated into planning in some sense. For example, if the like there must be some like ranges or errors of detecting objects or features using VLMs, right? And that kind of thing should be considered during the planning. But in the case of making representations or making like perception parts, I will not like fully like deep dive into the like uncertainty now, but I'll just accept that and we'll like put that into the planning parts. And if there's much uncertainty, there will be some like threshold reasoning, like for above this threshold, I'll accept this like labels, or below this threshold, I'll reject this label, something like that. That kind of reasoning I'll try first. But combining prediction, like uncertainty with semantic representation I think that's the next step to go.
Yeah, cool. I think that makes sense. I think doing like this probabilistic, uncertain semantics may be too hard. I was thinking more if there's just noise, like false classifications, how do the planners then deal with that? So you're not constantly switching between changing predictions or whatever. But anyway, let's maybe move on. Second question, yes, on that, the communication exploration, the part in the middle.
Yes.
So I think I'm starting to get a better idea. We've discussed this before. I'm starting to get a better idea of where you're going with this.
Do you have any specific slides you want to go?
Not really, but let me just ask a general question. So I think particularly this dynamic rendezvous estimation part, which, yeah, I think you had a slide on that somewhere.
Yes.
Like I think this is quite an interesting problem, very challenging problem. And I think you've identified some challenges and an interesting idea of how you might approach it. So my question here is, perhaps can you tell us a bit about what challenges do you foresee once you do this? I know this is proposed work. Well, once, a few months from now, once you're actually doing this, what challenges do you think will come up that will make this hard?
Yes. I think the biggest challenge about dynamic prediction of likely rendezvous points using prediction is that it's really the uncertainties are compounded across multiple rollout steps. For example, we are feeding the predictions of other robots into our observations, right? And re-predicting using that new observations, right? And that will like there must be some errors in the predictions, but that will be compounded across like multiple steps of rollouts. That will generate more like high scale uncertainty in the long term, I think. So the first thing that I will try is using heuristic based decisions. First thing that the reason why I'm saying this is heuristic based decision is that if there's a predicted map and we can still make the robots to predict other robots trajectory, and we can also make the robots to estimate other robots, when will that arrive, given the time and the distance and so on. But this might fail in some cases, right? And then the alternative option that I have is to have learning-based strategy where it directly outputs the potential locations of the rendezvous, which is trained from like some multi-robot, like frontier-based exploration or other explorations without communication constraints, but it can still gives us good areas of rendezvous point in the middle, right? Also, this learning-based strategy, if we want to like train this approach, then it could also be conditioned on the communication range. For example, I proposed 2 different communication range models, but it could depend on the communication range. So this kind of settings, like which conditions to consider and which is the better metric, better way to estimate rendezvous between heuristics or learning-based strategy. I think that's the key challenge of this chapter.
Yep. Cool. All right. Thank you. Yeah, I think, as you said, there's going to be like these compounding errors on top of each other. And I think what I can foresee happening is robots will end up going to rendezvous points and they're waiting for each other or whatever else. So trying to, if considering those fail cases, coming up with solutions to that, I think is going to be quite challenging.
Yes.
But I'm interested to see, how you end up solving that.
Okay.
All right. I think I'll leave it there. I'll stop asking questions, pass it on to the next panelist. Thank you.
Thank you.
Next, we will have Micah, second closest.
Thanks, Basti. Hi, Seungchan. Can you hear me?
Yes.
Yeah, thanks. First, just want to say it's been a pleasure working with you these last few years. I've enjoyed seeing you grow from we met early in your PhD till now nearing the end. So it's been a joy being on your committee. I think I want to focus mostly on the proposed work and then the semantic exploration.
Yes.
So first, maybe an easier question. I think you divided the semantic exploration work into you have a sort of a leader robot that's responsible for coarse exploration and
Yes.
coarse semantic understanding of the environment, and then some other robots that are responsible for finer exploration. And one thing I was wondering is if you're planning on including reasoning about how finely you need to perform the exploration task to answer a question. If you can ask where the house is, then maybe you already have that information, or if you have a mug inside the house, maybe you have to search really finely. And I don't know if you'd remember it from Fadil's paper, but they had a feature where they could either passively explore or more actively explore a room. And I was wondering if that's reasoning that's relevant to what you were wanting to do, or if that's sort of tangential to your plans.
Regarding the question about how fine-grained the local search robot can observe, I would say that there are in this chapter in the proposed work 2, which is given the structured text prompts using VLMs and having heterogeneous task allocation between robots. For the granularity of the leader drone, the region of interest should be much bigger than just house or building. It should be something like parking lots or forest or near the lake, something like this. It should specify the areas that each robot can go, right? And as for the actual local fine-grained search task, there's no limit. There's no lower bound of robot cannot search, but something like mugs or very small objects are not very apt fitting to the search and rescue scenarios. I think the most probable response would be something like find humans or find cars or find something that has some size of decently, not as small as very small objects in the indoor environments, because we are addressing outdoor environments, and also there's some concerns regarding the speed of the drones at the same time, and that I hope that answers your question about the granularity of the first chapter. And what is the other question again?
I think that was the main question. So by the sound of it, it seems more that the granularity will be more driven by engineering decisions,
Yes.
than reasoning on the back end.
Right. Yes, at least for this chapter. This is a chapter that heavily relies upon the prompts text that were generated from humans, which in this case I will give those prompts to robots. But I hope to address this question in the final chapter.
Gotcha. Another question is, I have a few questions related to there's a kind of a big jump between the like more geometric exploration or the spatial exploration chapters, the semantic exploration chapters. And I think the first question I want to ask there is like what's going to be like reused? How are the first chapter is going to contribute to the last chapters? Are we going to see like the map prediction applied later on, or
Yes.
like I don't think you've used room decomposition since you first published that. Is that going to come up later? Maybe you could tell us more about that.
So as for that parts, for example, I used like techniques like geometric tree extraction, but that was never used in the following chapters, right? I could have used that for like, for example, map prediction because it's similar indoor explorations, but I didn't have a chance to combine these two different ideas into one. I think that's one of the limitations of my thesis proposal. I think that said, the later part, which is semantic representation part, is more on the outdoor scenes. But it doesn't mean that semantic is corresponding to the outdoors. There are many good, great like semantic works in the indoors, but since the environments are vastly different from for the last two chapters, I think it's really hard to combine the first ideas into the outdoor scene like representations. Also, as for the prediction part, I think that's closely related to the question from Graham. Like how can you like combine the idea of predictions or uncertainties to semantic representations? That's a great question, but I think combining such like reasoning on the uncertainty or like probabilistic nature of semantic representation, I think that's great future research work. But given the time that I have like until the graduation and status of my proposed work, I think that should be like considered later, like for the future works. I hope that answered your questions.
Yeah, I think so. Yeah, so then the follow-up question, or like the other line I think I wanted to explore is you didn't talk a lot about like contingencies or different options you might have. So it sounds like the last two chapters are going to involve a lot of work. There's both planning questions and really big questions about like how you construct your representations.
Yes.
And I wanted to ask if you've thought at all about any contingencies you might have, like maybe there's open source packages that you can use. I know there's also like systems being developed by other people in the lab that you might depend on.
Yes.
So like, are there other pathways that this could go down? And like, what are your most critical dependencies?
Let's divide the first chapter and the second chapter. As for the first chapter, we are planning to demo the single robot demo first, and we are like collaboratively working in the lab along with me on the single robot hierarchical task using VLM features until next March for our sponsors. And that closely relate to my research, which is just adding like multi-robot. I mean, adding another robot is huge work, but I think the pathway towards that is already there. As for the final part, which is online semantic scene graph, I'm a little bit more flexible on whether we can actually run this on the on the Orin Ajax, like both VLMs and LLMs at the same time. The contingency plan is to, I think, in terms of like algorithmic or like framework wise, even like multi-robot online planning in indoor environments is a great research problem, and doing in like simulator like habitat or like big environments in indoors is also a great problem, and nobody has addressed this question yet. If that could be a continuous plan, I think, regarding that chapter.
Right. I think I'll let it rest there. There's a few other questions that I might ask later if we do a second round.
Okay.
I feel like you're technically, no, I'm just kidding. Trying to figure out if there's some way that we justify being further away or closer. Yeah, so some of my questions are actually related to things that have already come up. And I'm trying to decide if I want to press on them or not. I think that like maybe one thing that I'll press on, even though it did already come up, is in the earlier work when we're talking about uncertainty.
Yes.
What does it mean to be well calibrated?
well calibrated in terms of like.
So I think there's this notion that like, if I'm gonna have uncertainty, I have to, I have to be able to quantify that in some way, right? And so like, when you're looking at your work and you're like, oh yes, we now have this uncertainty, we can reason out this uncertainty, like, how do you know that that's useful uncertainty? Like, I could just do, a random model, it could produce a distribution for me, right? Like, that's not useful.
Right.
I could have an overconfident model, which would give me, you know, which is also not useful. So like, what is it, how can you tell if your model is actually well calibrated in terms of its notions of uncertainty? And then, like, is that evaluated or measured somehow? And
We're asking like how, okay, I would say in the context of like the very map prediction based commercial work, like well calibration of uncertainty, like it depends on the models. Like for example, in other works they use like linear networks for their own uncertainty predictions. In our work we leverage llama independent network, which is kind of arbitrary choice that makes sense. But in terms, if you ask if this uncertainty is real uncertainty that we're interested in, I think I would say that's one of the shortcomings of my previous work. And there can be some like more advanced works leveraging more advanced techniques, like for example, diffusion models or diffusion policy, that because that's inherently generating more problems or distribution of uncertainties given the models. You can generate more like full representations for the map. I think that's it. I didn't try that yet. I think that could be tried later, but for this moment, I didn't like exactly calibrate which is whether this llama model is good. But I would say I think this is a good predictions given the floor plan data sets, given the simplicity of the floor plan data sets. But if you're trying to work on more complex or diverse set of environments like outdoor scenes or not just occupancy based indoor floor plan, I think we need more rich representations that can handle more actual uncertainty that can explain the real uncertainty in the real environments.
should uncertainty be captured at a pixel level or semantic level?
It would be good if we can capture the semantic or more global level of uncertainties, because one of the shortcomings of our map prediction work was that we did pixel-wise variance of the predictions of maps to define the uncertainty, and that was a norm that was defined in the map prediction-based exploration community. But I think there are many criticisms against that. For example, in this case, the uncertainty was measured by the variance of the predictions. But for example, very far away from where robot the robot can't even like predict at all, right? In that case, the variance could be low, but it can still be very uncertain, right? So in that case, that like mismatch between variance of the pixel-wise predictions and like uncertainty might be mismatched. In that case, we want something more than pixel-wise uncertainty, but we want more global level or semantic level. But I haven't thought deeply about it yet, so that's my answer.
So in the online semantic graph, this is gonna wrap back, but in the online semantic graph, how do I deal with conflicts between the predictions of two different models? Two different robots?
So I mean the predictions of two different
So they have to merge their maps,
they have to
right?
anyway merge their maps.
Right, so their detections are, you're gonna have detection errors, segmentation errors, everything else, right? So what happens?
So so we'll follow like, so each robot has its own like predictions of each robot runs the same like VLMs. Let's say NetClick, for example, it will generate dense VLM features from each perspectives, and it will generate like positions of the graphs, position of the objects or like chunk of objects, right? And that will have some sort of errors and I think, and that will be for now. I just said that I will just put the like 3D position or the bounding box position of the objects or bounding box positions for each graph. But in that sense, if the robot has, well, let's think of two different steps first. If the robot are exploring completely two different environments, for example, in that case, merging isn't super conflictive because each robot is exploring different areas. And the case, what matters is the case where two robots are exploring in similar areas or some overlapping areas where robots can have two independent observations and generate its own projections, right? In that case, we have to think about like how we could fuse different like information into one representations. I think there are many like methods like I think I'm not sure whether this is applicable to like VLM or foundation model models, but in the case of scene graph, like what people usually do is like fusion of the information, such as using Bayesian updates or like more probability updates of how where this information is lying, and combine them using such like more probabilistic nature using like Bayesian updates. I think that's one option. I'm not sure for the like foundation models yet, but I think that's how other works like that investigating multi-agent like scene graph.
So do you think those updates should be happening at not pixel level in this case, but the bounding box level or at the semantic level, or is that a meaningful distinction?
I think I don't think pixel-wise level is meaningful at this point because it's too fine-grained. In that case, it's not pixel level, it's a box level. I mean, box level is too fine-grained, I think we should like capture some more than like that, like more global level, at least object level or like area level, predict like semantic. Yeah, I would say the pixel level or box level, that's too fine-grained details.
So I have the same problem, right? So I have, how do I know if it's calibrated uncertainty? So I have, whether it's for the earlier stuff or for here, I have two different agents.
Yes.
They both are observing the same thing. Their odometry is slightly different. The detections have some amount of error in them, so on and so forth, right?
Yes.
Adding them together is not the plan. Does one of them, but each of those models is giving me maybe distributions or other kinds of properties like this.
Yes.
So like, do you have thoughts on like how I could actually?
Like adding doesn't make sense because
Yes.
But I think like the simplest way to start is to average the like whatever output they have. For example, if they have like this like locations and that location from other robots, and just simply averaging those two could be starting point, I think. But there must be a better way to like average than that. Like there must be a better way than just averaging them. Maybe like weighted average or like updates using like probabilistic, like as I said, Bayesian updates, something like that.
Yeah, I feel like I'm afraid that Bayesian updates is being used as a magic wand when what you're saying is I have two samples and then like that, I mean, okay, anyway, I won't be super annoying, but like there's like a thing there,
Yes.
right? That we probably want to, okay. You also mentioned that you're assuming you're gonna have these complex prompts potentially that will go to the LM.
Yes.
So you gave examples, you were like, well, I have simple ones and I have complex ones.
Right.
The simple ones came with paired examples, which was like, go to X or something like this.
Yes.
The complex ones did not come with a paired example. So can you give me an example of what, maybe I missed it, what is a complex?
Okay, I didn't add in the slides, but I have
Okay,
backup slides. Sorry. So I think I thought this prompts are complicated enough in like yes, for example, like find all obstacle paths around the lake. In this case, the robot has to find first like all the obstacle paths, and then has to reason over what's the path that's near the lake or something like that. Or
and so what's the expected output from the LM for one of these?
for example, let's say that although, for example, in the third prompt, like locating all exits of the red building, for example, like there can be many different notions of exits. And for example, if the prompt was given to the LLM, such as locate all exits of the red building, the LLM I think it cannot like directly generate like waypoints from like this prompt itself, but it has to go through like at least two-step or multi-step reasoning over what that means. Like what it first has to do something like it has to first like find some areas near the red building and then try to find exit doors or points out exit areas that correspond that in the building. That kind of like reasoning that requires like at least that's not single step reasoning, right? That requires at least two-step reasoning for the LLMs.
So is the goal that the LM is going to generate code with this logic specifically in it, or is the goal that the LM is going to produce a natural language response, which is the series of quote unquote reasoning steps necessary to identify?
So it depends. Like it depends on. So I think the the output format.
Yeah.
Output format of the LLMs is quite tightly coupled with the what kind of graph structure that I'm trying to build at the same time. But it can be divided into like simplicity of text prompts. For example, if that text prompt is something that can be answered as a single text answer, I want the robot to answer the question as a single answer. But if we want the robots to actually take some actions, then it should generate some waypoints, right? And in that case, we want the LLMs to generate like output of subtasks and the potential actions that it can generate
Right, like, can you give me an example of those, that subtask that it would generate?
from LLMs.
Yeah, for example, for locate all the exits, I think was your example. So what's the subtask that you would want it to generate when it gets that prompt?
Like in the case of like locate all exits of red building, the first thing that it should do as a subtask is that it should like first find a subtask that tries to detect red buildings near in the environment, and then the robot has to start finding the locating all exits of the red building, focusing on that.
Right, but presumably it doesn't have primitives for each of those concepts, right? So it needs to both define a set of concepts and then it needs to define a series of function calls or something like this, or waypoints in order to do that. So then my concern is that means the LM basically has to run a search algorithm.
Yes.
Do we think an LM can run a search algorithm?
I think like the most advanced version of like, I would say it's search algorithm, but it's more like a chains of reasoning within the LLM, or like there.
I get what you want. I'm just saying, like, I'm not sure it's gonna produce what you want, and so I would maybe argue that you might wanna think about using code or some other thing like this.
Yes.
So for example, if locate all the exits turned into some sort of like a for loop or a
Yes.
while loop or something like this, that gets us a little bit closer without you having to have the LM quote unquote execute a loop, right? Which I'm not so convinced it would be able to actually do. Anyway, but then, the reason I'm asking is I'm not sure whether or not your goal is to have it produce something like this, which is basically a task plan that it can then execute, which is fine, so we have some set of primitives. Or if your goal is to have it output the waypoints or a sequence of waypoints or something like this, which is closer to the simple queries. But in that case, then I'm gonna go back to my same question, which is, I have a bunch of waypoints that are getting scored by this model, and I have to decide if I'm calibrated to determine which ones should be included or not.
Yes.
So I end up, I'm back in that same calibration, question, and so I think you may want to to be clear, I'm not expecting you to solve uncertainty. Like, it's like not a thing, whatever, but like, I think that there are all these places where it is going to show up again and again and again throughout these works, even though they're not explicitly mentioned.
Right.
And so having some working definition of what your comfort level is with how you define thresholds or something like this is probably useful for then sort of simplifying all these things. Okay, I will stop because I'm already being annoying.
So much.
Great talk. I just have a few questions. So, on slide 68, which was your fiction and uncertainty of this work,
Yes.
you're proposing to do this all in simulation.
Yes.
No, nothing tested
On the real robots.
on real robots. It's proposed works 2 and 3 that are going to be tested on real robots.
So proposed two and three will be definitely for the real robot, the asynchronous that we are building. As for the proposed work 1, it's tightly coupled with our plan for the completed work that I collaborate with Sherry, and we are trying to extend this to journal paper first, and then we want to like do some like not drones, but like ground vehicles based exploration in doing
Oh,
this
okay.
first. And then if time allows, I will try like real world experiments with ground vehicles on the multi-level settings. But I think for iOS level, I think I'll just go with simulations first.
Okay,
Yes.
so. Or will you get this tested on real robots or not? Like, I'm still not sure.
We
So it
haven't
is yes,
we
right?
haven't tested or built on vehicles for even the single robot yet.
Okay,
That's why I kind of dream before I graduate.
so the answer is no. Just simulation only. It's okay to say no.
Just simulation only.
Just
Yeah,
figure out what's going
just
on.
simulation only for this middle chapter, I would say. Yeah.
Okay, so we'll assume no for now. That's fine.
Yep.
Okay, cool. So the one. So I'm a little bit concerned that there's a lot of work.
Yes.
That's where my line of questioning is coming from, and I think Micah might have hinted about the same thing too. So can you go to your thesis statement?
Yes.
Cause I feel like you're proposing two separate systems.
Mhm.
And there's a lot of work here, so I'm afraid that so I guess, how do you see that work? The proposed work one fitting into this thesis statement, because there's one proposed work that's gonna be tested in simulation that has the map uncertainty component of it, and it's multi-robot, but it only considers the spatial reasoning aspect. There's no and then there's this proposed works 2 and 3 that have the semantic aspect of it, and that's gonna be tested outdoors, and that seems like a separate system.
Yes.
So it seems like there's 2 systems in this thesis statement, and maybe that's okay. It seems like you're proposing
Yes.
a lot of work for the given timeline, and I'm a little nervous.
Yeah, thank you for the great question, and I will accept the criticism, if that's criticism, that this is kind of 2 branches.
Okay, okay,
One is more spatial reasoning, and other one is semantic representations.
okay,
And but at the end, all our purpose is to improve multi-robots in some sense, whether that's task allocations or communication constraints. Our goal is to improve either exploration efficiency or success rates in the navigations. And it would be either spatial or semantic representation, and I couldn't combine these two into one yet.
Yeah.
But given the time that I have until graduation, I think combining this all together, I think it's not achievable.
yeah, I agree with that.
And then it's a 2 different system, I would say. And given the timeline that I have, I would say, I think your concerns might be the last part of the semantic representation, because that's more related to real world placement from now on, right? And that we as a team in the lab, we are building new tools at the same time. We recently developed Airstack Simulator, which is ready to work on. And the only thing that I can start from now is to add the planning components into that, add running VLMs on the running with those Airstack Simulator at the same time, combine that into semantic representation pipeline, and think that's doable, I think, because we are anyway doing demos for single robot by next March. And I think for the next 4 months, I'm going to multi-robot aspects of that, and we'll spend 7 months with the last project.
I guess my only criticism of this thesis statement, given what you said, is maybe cut in diverse environments. If you give 2 systems, and one is being tested indoor, and the other one is being tested outdoor, you haven't given a list that, unless you're planning on testing a bunch of different variable outdoor environments. It might be easier just to cut in diverse environments. Okay, cool. So my next question is, so you can go to slide 85. And I'll try to be brief. We're almost at time.
Yes.
So this, you're planning on testing allocators, right?
Yes.
Okay, and this is. There is some centralized aspect to this, or at
Yes.
least you're having to go to a ground station, or are you thinking about doing this? The prompt receiving, is that happening
So that's the prompt is given from the base stations.
yeah, okay,
And
that's,
that could be thought of as a centralized, but it could be thought of it's not planning of how robots are doing, right? So I would say this is more hierarchical, decentralized planning. And it's not distributed setting, but it's definitely decentralized.
have you thought about lengths and the kind of scales that you're gonna test over this, and
How much-
is stuff gonna drop out? Do you see what I mean, when you're testing outdoors or even, indoors, it's like conflict sprigs, how are you gonna talk to I guess I'm a little nervous about. I didn't see enough specificity in the kinds of real world experiments that you would be running in order to this is. How tractable this is gonna be, use a Silvus network system, are you gonna use Wi-Fi, what is that?
So we're going to use and for the communication purposes, sorry. Sorry for
or LTE?
I think we are using radio communication with hardware called Webs, yeah. Which provides wearable mesh radio. This is being built right now.
Oh, I'm very familiar with Google Apps.
So,
Okay,
uh,
great. Yeah, and the dual communicates to some base station and then
Base
have to
stations.
have an internet connection.
Yes, yes.
Okay, cool. That's helpful. And then, okay, yeah, if this is all being handled by Google Apps, I feel like. Okay, I think that you have a big plan for actually how to execute these experiments. All right, then, that's all I have.
So I'll also try to be quick, but, just wanted to come back to the uncertainty a little bit. And actually, in a different sense, like similar to what Graham was asking, is that in your previous work, and I think in your proposed work also, the uncertainty will drive the actual policy. Right, so if you say, hey, I find red car, but it's that I don't know about the red car, then I already look for it, right? So really think about this. And then we do it. This was one of the question. Similar for 68, I think this dynamic rendezvous part, I think it would be really nice if you could come up with a method that has some guarantees. It's not just futuristic. Whatever that could be.
Yes.
And I'm sure you can come up with something that will, work in some cases.
Yes.
But it would be good if you come up with something that can guarantee that there will eventually be.
Yes.
Um,
With regard to that, I think still we'll dynamically update likely rendezvous, but we'll still have some like backup plans. Like we cannot avoid like robots waiting for few times. That I think that's such kind of like safety policy that should be there. I think for automation.
Yeah, I think we'll have to talk a little more about like how do you actually have a guarantee it, right? And how do you make sure that it's like all this happening, and the other one is the role assignment, the number of robots in the drone. And so I was just wondering, what happens if that drone drops out, or what happens if you get a new drone? How does that all?
So I think working drone is less important than leader drone, I would say, in this case. So if working drone drops out, or if we add another working drone, I think that's fine, not a huge problem. But if leader drone, which performs global segmentation in region of scouting, if that fails, that's completely a new story, I think. So in that case, we should have some sort of plan for that. For now, I'll start with leader drone is fine first. And then that's failing, then we need our task reallocation.
And then are those drones homogeneous, or?
So these drones are homogeneous in terms of like perception capacities, but it just has homogeneous task allocated.
And then I just wondering, a small technical, so where do you expect the LLM to run?
So we are trying to, so that's a great question that all of me and my teammates are trying to address over the past few months. So we're trying to run DLMs and LLMs possibly in the Ring Ajax, and we try to like throughput analysis of whether that's more like that's acceptable in the Orient Ajax, which is in the drone, right? So many encoders are we're able to use this DLMs or LLMs encoders Orient Ajax, and it depends on the like resolutions and everything. But LLMs, in the worst case, will if Orient Ajax cannot be run on if LLMs cannot be run on Orient Ajax, then we should reframe the problem into a setting where it can be run at the base stations. But first, we will aim for Orient Ajax segments. Okay.
And then I just had for this whole question about what do you want the LLM to do? what I would have expected is maybe you say, okay, we're gonna use that graph structure and basically. Essentially, teach the LLM the graph structure, and ask it on that graph structure to come up with, the things to do. Was that how you were thinking, or like, I didn't see that link between the complex task and the CMU.
So at this point, I'm quite open to different possibilities of what kind of graph structure. I think the first way I want to leverage like should be like hierarchical structure that LLMs can leverage such hierarchical like purposes, hierarchical semantics, or are we just using like something like concept versus for multiple versions? Depending on the choice of the graph structures, I think the prompts, the way how LLM processes those inputs as a graph, it becomes slightly different, I think. I think as I do more like research on during the research, I think it will be more clear, like as I work more scientific.
Yeah, more like what we can talk with. Brad, Micah, do you have any more questions?
No.
I had one other question I was wanting to ask.
No questions?
Huh?
Do you have questions?
I had one other question I was wanting to ask. So one question I kind of had was basically asking about the value of map predictions in the completed and the proposed work. So I don't think you showed the ablation experiments for the map prediction paper.
Yep, I didn't
Yeah.
actually slide, but I have a backup slide that shows. Oh yes, ablation studies of MapX, where we eliminate each component of like should be deterministic raycast or probabilistic raycast. Should we have sensor coverage or variance? Should we just use observed map? That shows this graph shows the. So our MapX algorithm outperforms other evaluation methods, and which shows that we don't need all components for MapX.
Yeah. So when I looked at this, my takeaway was like first, like I looked at this and then the comparison to the baseline. So like your approach did significantly better than the baselines on the experiments. But then when you go to like the ablations, there's real small variations in performance, even if you like turn off the prediction components. And like you only see that like really big jump in performance when you like turn off the visibility, or I think that's the ray tracing. Is that right?
Yes, the visibility was the key component of our
So looking at this now, like the conclusion that I'd come to is that maybe there's like a small impact from
uncertainty.
Or from like prediction in these experiments. And there's like one question like Jonathan was asking about was like the question of calibration, and maybe you could also ask like if you had perfect predictions, how well would you perform? Or if you had a better models of uncertainty, how well would you perform? But like the question I want to get at, and this comes at kind of stuff I dealt with in my own thesis, is like how much value is there actually in prediction on this problem and then on the other problems you're studying? So like in my work, I spent a lot of time looking at doing local joint planning for multi-robot teams. And I fought with that through the whole duration of my thesis. And like the conclusion I came to at the end was that I could do good theory, but that at least for the problems I was studying, there was a very small impact on performance in practice. And the first thing I want to ask is like, is this maybe the same thing going on, at least in the context of this paper? Like, is there only like a small amount to be gained in these like office environment exploration experiments, or maybe if you reframed it differently and looked at a slightly different setting, maybe that'd be more value from prediction? Go on.
Yeah, so you might just seeing from this graph, you might think that the gap or like gap between, for example, between map X and observed map, which doesn't use prediction, is not super high, right? Like
Mhm.
observed map just use observed grid, but in that in fact, the observed map was the like hardest benchmark that we had to beat while we were doing, because it aggressively overestimates the information gain. It just goes so fast, right? And I would say the MapX, by leveraging both coverage and uncertainty, shows much better performance than observed map or any other. For example, the green curve here is deterministic, which is not using probability raycast, but just relying on the deterministic raycast, but with predict map. So it shows that there's, if you compare the red and green curve, you clearly see the difference between probabilistic raycast and just like deterministic raycast with underestimation of information gain, I would say. And for FYI, no visibility means that there's no like reasoning on the sensor coverage, potential sensor coverage, but at the same time, our sensor coverage is also dependent upon the predictions. We are not generating visibility mask from the observed map. We are generating that from predict map. So we still need predictive maps for generating to tease out the strength of visibility masks.
Oh, wait, what was the last thing about visibility mask?
So the no visibility, the yellow curve is the lowest like evaluation basically, right? That was just using the variance or the uncertainty, which is quite similar to the UPenn baseline, right? But from here, what bumps things up, like what boosts a lot is the existence of the visibility mask, which can be generated from both observed map and predicted map. And the existence of visibility mask is a key that improves the curves. But even with that, I would say having both probabilistic raycast and visibility mask is the combination of these two is the thing that that shows the best performance. Although it might be like super large, but it's an average of 40 different floor plan data sets. And if you average that, that's in terms of behaviors and qualitative behaviors, that's a huge difference.
So to follow up a bit, it's I don't so much want to focus on like the variation in performance here. Like to me, it seems like I don't particularly care if like to me the question can be answered either way. It could either be a small impact or it could be a large impact, and you study that, you run experiments, you take those conclusions and you move on. And I think the ultimately thing I want to get at is now you're planning on doing another work that builds on this, and I think it's worth asking, how does prediction fit into then the communication paper? And so for one, maybe it just turns out that there's a small boost compared to like the observed map in MapX here, but maybe there's a regime where map prediction is very helpful for predicting the rendezvous points.
Right.
And to me, that's still a fuzzier thing, but I think that like broader, like, I don't know if it's philosophical or scientific question of like the value of the prediction in this domain is worth like thinking at a very high level as you move on.
Yes. Yeah, I'll definitely consider the predictions and uncertainties into considerations into generating like estimation for dynamic roundabout points, as you said, because we should see the benefits of having predictions and uncertainty estimation compared to the observed map, right? In this case, the gap is, it might not be too big. We don't know yet, but I think considering that is a key, I think.
And I guess the last thing there is it seems like that's going to be like really sensitive to like your communication range, right?
Yes.
Like if there's a small communication range, then you're just going to miss the other robots and you won't know if it hasn't gotten to you yet or if it just already explored and is way past you. And I imagine that's something you're going to have to fight with in designing your experiments.
So
is that kind of like the right thinking there, or?
no, you're right. And the range could be different. So I'll first, the thing that I'll have to test is first, the reference is the real robot. So cannot exactly estimate like where the communication ranges are, right? So we want a very rough estimation of where the communication can go. And the circular range is just simplified versions of communication range. And I have other model that considers the blockage or number of occupied cells in between. That's another model. Having that said, there are some works that did this similarly, like doing both. So I think that could be a reference that I can take.
Okay.
Yep.
I think that's all the questions I wanted to ask.
Great. Okay, let's stop.